In this tutorial, I'm going to talk about how to derive the vector potential for an oscillating dipole. There's a very strong parallel between a problem we can solve in electrostatics and the problem we want to solve now in electrodynamics, and I'm going to try to emphasize that throughout this tutorial. In electrostatics, here's a problem that we deal with all the time. Very simple problem. We have a point charge, and I will put a little dashed region around it to say that, look, it doesn't have to be an exact mathematical point, but there's some small region of space where all the charge is enclosed, and that charge has a total amount q. This might be an atom, for example. And then at some point in space that's outside of that region, we have another point. It's located by a vector r, and we want to know what is the electric field there, and since electric field is derivable from a potential called psi, we can ask what is psi at that location. And once we know what psi is, the scalar potential, we can figure out the electric field there by simply taking derivatives of psi, in this case a gradient. So that's an electrostatics problem that we see all the time. Now in electrodynamics, you can have a similar situation, and that's what we should be talking about around the time you're seeing this video, which is that we can have a little point charge that's oscillating back and forth. This is the electron cloud of an atom shaking back and forth in time as a light field shakes it back and forth. So similarly, we can define a certain small region of space where all the charge is contained, and it's shaking back and forth. So it has a total charge q. But now this is a dynamics problem. This charge has some velocity v, and the velocity is changing with time as it sinusoidally shakes back and forth in sort of simple harmonic motion. Now we can also ask the question, okay, here's some remote point. It's again located by a position vector r from the origin, and we can now ask, instead of what is the scalar potential in electrostatics, we can ask what's this quantity called the vector potential. The vector potential is a function of position and also of time because it's a dynamics problem, and that's what we want to know now. What's the vector potential? Why do we want to know that? By analogy with finding a scalar potential and getting E in an electrostatics problem, now once we know the vector potential, we can now find the magnetic field by taking derivatives of the potential. In this case, it's the curl of the vector potential. And ... means we can go off to the races and find out other things like what the electric field is as well. So two very similar problems. What are the governing equations that we have to solve? Well, these are the master potential equations that Maxwell's equations give us, which we should have talked about already by now. And I'll remind you what they are. There's del squared of psi minus mu naught epsilon naught, second derivative of psi with respect to time, equals negative charge density of rho, charge density over epsilon naught, and the other three equations that when you write Maxwell's equations in potential form are for the vector potential, and they look exactly the same mathematically. They also are del squared minus mu naught epsilon naught second time derivative of the vector potential, and that is equal to negative different universal constant mu naught j, the current density as a function of time and position. So these four equations, remember these are three equations because it's for a vector, these are Maxwell's equations. So they equally dictate what to do in this problem and what to do in this problem. Now in the case of the electrostatics problem, nothing is varying in time. So this term goes to 0. Sorry, I should have put a square there, not that important. So that term goes to 0, and that means we get a simpler equation, del squared of psi simply equals negative rho over epsilon naught, because this term here equaled 0. What about over in this case? Well, I won't go into it in full detail here, but this term I'm just going to put a dashed line through because it doesn't entirely equal 0. But when we are considering positions r that are within a wavelength or so of the origin, this atom is much smaller than an optical wavelength, so we can be in a region that's close to the origin within a wavelength and yet not within the charge region. So if r is much, much less than the wavelength, if we did further analysis, I could convince you that these derivatives, this term becomes much smaller than this term, and we can neglect it. And that allows us to approximately say in that region and that region only that del squared of A in when r is much, much less than lambda, that's approximately equal to minus mu naught J. So we still got a very parallel set of equations between here for electrostatics and here for electrodynamics. Let's now march off and actually solve this equation, because we actually, from freshman physics, know what the electric field is of a point out here if there's only one point charge at the origin. One way to see that is to recognize that since E is the negative grad of psi, this equation here in electrostatics is nothing more than saying del dot E equals positive rho over epsilon naught. And you should recognize that as Maxwell's first equation. And we know what the solution is for that. I'll remind us that the point source solution is that E at that location R is the total charge over epsilon naught divided by 4 pi. Remember, electric field goes as 1 over r squared, just like gravity, and it goes in the r hat direction. R hat points in the direction of r. Now I can write that another way. I can rewrite the charge as the integral of charge density over this little volume near the origin. So I can write the Q as the integral of rho over epsilon naught integrated over the volume of that little ball, 4 pi r squared r hat. And what I want to emphasize to you here, notice that the rho over epsilon naught has gone into the integrand up here. And let me emphasize on the other side of this equation that electric field is equal to the negative grad of psi. So now that I know what the electric field is, I've got a solution for it here, and that's the negative grad of psi, it becomes pretty straightforward to write what psi itself is. Psi is a function of r. And that's just the voltage, and that's something you also solved for in an earlier physics class. So let's write it down. And you know that it's a very similar formula to this, except the potential goes as 1 over r. Keeping this idea of writing it as rho over epsilon naught dV integrated over that little ball at the origin over 4 pi r. So now, let's emphasize what we've done. We started with an equation for del squared of psi, and what we wound up with was a formula for psi itself. And again, pause here to think about the fact that this is stuff you know, you just haven't thought about it in terms of potential psi. We know that if there's a point charge at the origin, that the electric field here goes as 1 over r squared, and then we learned that the voltage, or the potential, goes as 1 over r. In the numerator is simply the amount of charge in the ball. It's Q over 4 pi r. I'm writing it this way to emphasize that the right-hand side of this equation, rho over epsilon naught, showed up in the integral in the numerator here. Now we're going to go by analogies over to the other side. Now remember, that's really 3 equations. let's write them in x, y, and z. So one of them, here's the x component of the left-hand side, and we are saying now that that's equal to negative mu naught x component of the current density. There's also an AY and an AZ equation, JY, JZ, everything else stays the same. So I've got three equations. Well, I'm going to put a box around this equation, this first one, to emphasize that it's got a lot in common with this equation. It's del squared of a scalar field, negative constant times some other scalar. So I can now assert that the solution to this mathematical equation should be mathematically formally identical to this equation's solution, because they've got exactly the same form. I just have to take that right-hand side and put it in an integral. So the argument is that the vector potential component a sub x in the range where r is much, much less than lambda what should it have? It should have a 1 over 4 pi r, which I'll write out in front, 1 over 4 pi r, and then there should be an integral over a volume, and what's going to go in the integral is going to be this. Here it comes down. I'm going to put inside of the integral mu naught j sub x. Now exactly the same solution is going to apply for the y and z components of the vector potential. So if I wanted to add those three solutions together, I get equals 1 over 4 pi r times mu naught, I'll pull it outside of the integral, and then the integral of jx x hat plus jyy hat plus jz z hat. I'll skip ahead and write that as a vector j, integrated over all volume. And that lets me wind up with the following equation, that the vector potential near the origin is equal to 1 over 4 pi r mu naught integral of current density dV. And that's powerful. I'm going to put the box around this equation too to emphasize that we've now got a parallel solution to this. So we now have an expression for the vector potential in the neighborhood of the origin, which is exactly analogous to how we got our solution to the scalar potential. So what's the physical interpretation of these two steps? On the left-hand side, the physical interpretation of this expression is just to look at this integral and say, well, that's the total charge inside the ball near the origin. So I would just rewrite this as psi of r equals q over epsilon naught over 4 pi r, and I'm done. What about the other case, for the ball? I've got a ball up here. I expect my integral to somehow talk to me about q and v. And it turns out that if I integrate this integral, if I do this integral for charge density times a volume, I get exactly the units of current times velocity. Perhaps we'll work on that in class to see that. But the substitution actually follows very parallelly. And what we get sort of physically here is that the vector potential near the origin can be thought of as being the charge times the time varying velocity. There's a mu naught out in front and a 4 pi r underneath. And that's the physical interpretation of this. We're now almost done. The only problem is that we only know the vector potential near the origin. What's the vector potential farther away from the origin? Let me just clean up this blackboard a bit and we'll find that out. So here we are, cleaning it up again. So here's again our result for the vector potential when we're close to the origin. Let's think about how to write the velocity. We know the velocity is the time derivative of how the position is changing with respect to time as this little thing sloshes around. And in our particular case, we're considering sinusoidal oscillation, so that's going to be the time derivative of some maximum displacement, x max. That's a vector, so maybe x max is the maximum amount it moves this way, and then times harmonic time dependence, e to the minus I omega t. Well, x max, that's just a constant. So that doesn't have any time derivatives. That just comes out here as x max. And e to the minus I omega t, that just has, that of course the time derivative of that just brings down a factor of e to the minus I omega, and then we keep to the e to the minus I omega t. So this as a whole is equal to minus I omega times x as a function of time. We can then write the vector potential from above. If we just group all the non-time dependent terms together, we get mu naught over 4 pi r. Those don't depend on time. We have a q. We have a minus I omega. And then the only thing that depends on time is that position. That's still got the time dependence in it. X as a function of time will influence A as a function of time. Now this is true very close to the origin. Now we make an assertion. We want to find the vector potential at any distance from the oscillating dipole, not just very close to it. And relativity says that if you're a distance r away, you can't be instantaneously influenced by what's happening here as a function of time. There has to be a delay for that effect to propagate to here. So I'm not going to defend that rigorously, although the notes do defend it rigorously. What we're going to say here is now
we have to modify this expression so that instead of x of t, we're going to evaluate the motion that was happening not now, but at an earlier time. That's why I have a minus sign. And that earlier time, r over c naught, is exactly the time it takes light information at the speed of light to propagate from the origin out to location r. Now what is the motion at time x minus r over c naught? Well, the motion x is given by what's in these brackets here. It's x max, the maximum displacement, and then it's e to the minus I omega t. Well, now we're going to plug in a specific value for time, e to the minus I omega t minus r over c naught. And we can analyze this term further and write that as e to the I, and the first term is positive omega over c naught r, and the second term is minus omega t. That just follows algebraically from here. Omega over c naught is equal to the wave vector k. That's a definition that we've used a lot. And so this actually becomes e to the I kr minus omega t. And that's a form that should be familiar from a lot of places that we've seen stuff like that. So let's bring down the other terms here. We have an x max. Building to the left, we have a q. I'll write it next to the x for reasons to be seen in a second. And what's left over here is minus I mu naught omega over 4 pi r. So that's what our vector potential at any arbitrary location is equal to. This expression is good anywhere. And if I just group the terms one more time to make some emphasis, I'll still keep this minus I mu naught over 4 pi. Okay, those are all constants. But now let's emphasize the other dependencies here. We've got an omega. So the vector potential is linearly proportional to omega. Then if I group these two terms together, a charge times a separation, we give that a special name. We call that a dipole moment. And since that's just the maximum strength of the dipole moment, we're going to talk about dipoles a lot. So Qx max I'm going to write as dipole, maximum dipole moment P naught. And then I'm going to take the r from over here and emphasize the spatial dependence to show you that this is a spherical wave, e to the I kr over r, as you'd expect since it's a point source. And then I've got the time dependence, e to the minus I omega t. So there is our vector potential for an oscillating point source, which is to say an oscillating little dipole. Constants, omega p naught, e to the I kr over r, e to the minus I omega t. And now that we've got this expression, we're now ready to go off to the races and do what we want with this expression. Now that we have A, that allows us to take the curl of A to give us the magnetic field of the dipole. And then eventually we're going to relate the magnetic field to the electric field. That'll be done in future notes.